Hello everyone. In this video, we'll look at some more examples of trigonometric substitution. Since we've already covered the basics of this method, pause here and see how far you can get on your own with this one. And when you're ready, we'll have a look at the answer. So remember that trig substitution can be used anywhere you see a sum or difference of squares. And in this case, we've got one under the square root. And you can see that more clearly if you write it the way that I've just done. Next, we need to look at these three trig identities and pick out which one most closely matches our difference of squares. In this case, under the square root, I can see a variable squared minus a constant, and this third identity also shows a variable squared minus a constant, so that's the one that we'll use in this case. So our goal here then is to make the expression under the square root look like secant squared minus 1. If we assumed that 3x was the same thing as secant theta, that would be a good start, because then we would get secant squared minus 4 under the square root. But what we want is secant squared minus 1. So we need to modify our substitution to fix this problem. So instead, we'll let 3x equal 2 secant theta, and the reason for that is because this 2 would then also get squared to become 4, and that puts us in a position where the 4 can be factored out, which would leave us with the secant squared minus 1 that we wanted. After that, we can go ahead and apply our trig identity to get tan squared theta under the square root. And with that, we can now cancel out our square roots. So this is working pretty nicely, but we still have x's left over, which need to be expressed in terms of theta. So to start with, let's find dx by taking the derivative on both sides of our substitution. On the left side, the derivative of 3x is just 3, so we get 3 dx on that side. And on the right side, the derivative of 2 sec theta is 2 sec theta tan theta. After dividing by 3 on both sides, we can now see what dx is equal to. And now going back to our integral, we can substitute that expression in for dx. So we're almost there, but we still have this x remaining in the denominator. That's no problem though. We can always go back to our substitution and figure out what x is equal to. With some basic algebra, we can see that x is 2/3 sec theta. And after plugging that in, we've gotten rid of all of our x's. So all that's left to do now is simplify and get our antiderivative. So start by canceling these terms, and then check that all we have left is 2 times the integral of tan squared of theta. So we've boiled the problem down to this result, which is honestly pretty nice. But how do we get the antiderivative now? As a hint, you can think back on the strategies we talked about for mixtures of secant and tan. Pause and think about it if necessary. I hope you were able to see that it's necessary to apply this trig identity, because after that, we can pretty much just write down the answer. Both of these terms have antiderivatives which are known to us. So the only thing left to do is express our answer in terms of x. And just like in the previous video, we'll do that by considering a right triangle as you see here. We'll also need to know the sides of this triangle, and the key to that is noticing the substitution we made tells us what secant theta is equal to. In this case, secant theta would be equal to 3x over 2, and since secant is the reciprocal of cosine, we know this represents the ratio of hypotenuse over adjacent. So we can fill out those sides of our triangle accordingly. And then to get the length of the unknown side, we can apply the Pythagorean theorem. Notice this third side shows the same difference of squares we saw in the original question, so that is a good sign that we're on the right track. For our final answer, we also need to know the value of tan of theta, which we can now see as opposite over adjacent. So just form the ratio of those two sides, and then plug in that result as tan of theta. We also need to know what theta is equal to, but unfortunately theta doesn't represent the ratio of two sides, but rather it's the angle itself. So the best we can do is look back to the substitution we made and try to get the theta by itself. And that's done by just applying arcsecant to both sides. And so theta is arcsecant of 3x over 2. Just plug that into your answer and you're finished with this problem. Now let's try this example. Pause and see how far you can get on your own, and when you're ready, let's continue. In order to use trig substitution, we need a sum or difference of squares. And we've got one of those, which you can see more clearly by expressing the integral as you see now. After that, we look to these three identities and find the closest match for our difference of squares. In this case, under my square root, I can see a variable squared minus a constant, and that's most similar to this third identity. So let's make a secant substitution. So as a start, we can let e to the x equal secant of theta, because that provides us with sec squared minus 9 under the square root. But what we want is sec squared minus 1. So we need to modify our substitution in a way that allows us to factor out the 9. So let's instead make this 3 sec theta, because that 3 would then get squared, which would allow us to factor out the 9 as desired. So after doing that, we are left with sec squared minus 1, so our identity can be applied. And now we can cancel out our square roots, leaving us with just tan theta. But it's tan theta dx. We still need to change this into a d theta. So let's go back to our substitution and take the derivative on both sides. On the left side, the derivative of e to the x is e to the x. And on the right side, the derivative of 3 sec theta is 3 sec theta tan theta. Now, to see what dx is equal to, we can divide by e to the x on both sides. And this result might seem problematic because we've still got this annoying e to the x floating around. But on the other hand, we know e to the x is the same thing as 3 sec theta. So we may as well call it that, since we'd prefer to work with theta rather than x in this case. Now notice 3 sec theta can now cancel from the top and bottom of this fraction, which leaves us with this pretty nice result. We can plug this formula in for dx into our integral, and after simplifying, we're left with 3 times the integral of tan squared theta. And just like the previous example, we can handle this by applying a trig identity. We now know the antiderivative of each of these terms, so we can write down our answer at least in terms of theta. All that remains now is to express this answer in terms of x. And for that, we look back to the substitution we made and sketch out our triangle as usual. Our substitution tells us that sec theta is equal to e to the x over 3, and that's the ratio of hypotenuse over adjacent. So we can label those sides of our triangle as you see here, and determine the remaining side using the Pythagorean theorem. Our answer requires us to calculate tan of theta, and that's now just opposite over adjacent. We also need to calculate theta, which is not a ratio, it's an angle. So we need to go back to our substitution and isolate for theta. And for that, you can apply arcsec to both sides. And if you do that, you'll find theta is arcsec of e to the x over 3. After plugging these expressions into our final answer, we're finished with this problem. How about this example? Pause and think about it, and if you're ready to look at the answer, let's continue. In this case, there's a sum of squares staring us in the face, almost begging us to do a trig substitution. And that would work just fine. But in this case, a u substitution also works just fine. You can pause and check all these details for yourself to convince yourself of that. And in my opinion, this is a heck of a lot easier than a trig substitution, and it takes a lot less time. So this is yet another reminder of what I said at the end of the previous video, that I suggest you only use trig substitution as a last resort. Try to be aware of all the methods at your disposal and make the most intelligent choice about not only how to get the job done correctly, but also efficiently. That's all I'll say for now, so I'll wrap things up here and see you next time.